now let us look at after cracking, how do we design for it. So, the total torsional resistance that is coming from concrete capacity and steel contributions, which is Tc plus Ts. Now, what is cracking torsion? This is basically concrete capacity. So, this is concrete capacity in torsion, right. Now, the same cross section is going to offer resistance to both shear as well as for torsion, right. So, I have to have some kind of an interaction equation. So, let us say you have Tc is the contribution that is offered by the concrete in torsion, and let us say Vc is the contribution that is offered by concrete to shear resistance. And what is Tc naught and Vc naught? These are concrete capacities when they are acting independently. That means when there is no pure torsion or when there is no torsion or when there is no shear, whatever their pure capacities are, we call them as Tc naught and Vc naught. Now, again, so you see here Tc naught is the torsion resistance by concrete when your shear and bending is 0, and Vc naught is the concrete shear resistance when your this should be when your torsion is equal to 0. Okay. So, right. So, this torsion is equal to 0, right. So, based on the thin tube theory, I think we have already derived an expressions for this, in terms of ACP, PCP and so on. If you substitute those parameters, then you will find this thing. Again, this also can be expressed. So, this is a simple expressions for your cracking torsion, okay, or TCR, right. What is this lambda p? Again, that is also some kind of an amplification factor, like we have discussed previously. So, if your FCP becomes 0, then this lambda p will become 1. If FCP is there, higher the FCP, lambda p will be higher, that is going to increase your cracking torsional moment. So, that we have seen that. Now, what is Vc naught? Now, Vc naught, if you look at it here, there are two things, okay. The two things will come. You remember, so this is a pure concrete capacity in shear is minimum of Vc naught and Vcr, right. So, this is for flexure shear, okay. This is for flexure shear, and we have also looked at one more thing, okay. So, let us also define what are the ratios. Now, this T by V is from your shear demand, and it is taken as the load ratio. So, that means when from your structural analysis, typically you will be given demand M, V and T that is acting in the cross section. So, I take the ratio of T and V, that I am defining that as E. Now, so Vc, then I can take that as Tc by E, and if I substitute that in the equation 32 that we have this 32 in equation 30, which is here, then I can find an expression for Tc in terms of Tc naught as this, okay. That means, when a section is subjected to both torsion and shear, how much will be the concrete capacity in torsion as a function of torsional capacity when only torsion is acting, okay. So, because same cross section has to resist both shear and torsion. If I take that as pure capacity in torsion, then entire thing cannot be taken when you both shear and torsion is acting. So, this is, you can say, there is some kind of a reduction factor, right. So, this is some kind of a reduction factor, right. So, similarly, we can do that for Ts as well. So, same thing that we can do that for Vc as well, which is defined as Tc by. Once you calculate your Tc, then Vc is nothing but Tc by E, okay. So, in that way, for any given cross section, for any given demand, shear and torsion, I can find out Tc and Vc, okay. So, this is only for example, Tc in Vc naught, we are taking only this, but we have seen that if I am doing the cross section at the support location, it will be the web shear that will be mostly controlling. It is not the flexure shear. This is for flexure shear. There is one more equation that is there for, in fact, this is VCR, okay. So, this is for flexure shear. So, VC naught and VCR that we have discussed. So, I need to calculate both the values and I take the minimum as the concrete shear capacity in shear. Okay, now let us look at how do we find the stirrup contributions from torsional resistance, right. So, now the same stirrup is going to be effective for resisting both the torsional moment as well as for the shear. So, what we are saying is the AW, the stirrup reinforcement, I am going to divide them into two things, AWT which is effective in resisting torsion and AWV which is effective in resisting shear, right. So, what is AWT? Stirrups that are required to resist torsion, and AWV is the stirrup that are required to resist shear. Now, one thing that we have to note here is, we have seen, let us say if this is a beam, right, let us say you have shear crack like this, let us say I am having. So, this is a through crack. That means, whatever that crack is intercepting the number of legs, all the legs will be effective in resisting the shear, but that is not for torsion. You know that torsion shear stress is only on the outer periphery, and also the torsional crack is going to be spiral. So, the only that is, even if you have 4 legs in the cross section, it will be the only one leg that will be arresting that crack, right. So, the leg that is on the outermost locations is what will be effective in arresting. So, for a 2-legged stirrup, if you look at it, both the legs will be effective in shear, but will be only one leg that will be effective in arresting the torsional crack. So, this you have to take into account. Now, how do you get your torsional resistance from stirrup, which is given by this space stress analogy, AWT into S FW, this is a tension force, and then you take the lever arm and then you divide by the distance to get this component. Now, this factor is taken as 1.5. This is what it is valid for stirrup contributions. Again, the derivation is coming from your space stress analogy. Okay. Now, for shear, what is it? So, when both shear and torsion are acting, this is your stirrup contribution in shear. But if you go back, only when shear is acting, we have taken only this into Fy into d by S. Now, there is one more 2 factor that it is coming here. So, you have to, so this equation is modified when you have both shear and torsion. So, this is the equation that we had for Vs when only shear was acting, right, for vertical steps, that is for vertical, like only when this was there. So, we took this Vs as this, right. But when both torsion and shear is acting, this equation is modified into 2, because we have seen that when you calculate the total stirrups, it is a 2 legs. If I assume 2 legs, it is a 2 legs are helping in shear resistance, but in torsion it is only 1 leg. So, that is why there is some kind of an interaction that will happen. So, the equation has been modified like that. Okay. So, now again, what is that Vs? So, that means the same stirrup. So, we can write that as Ts by E. Again, there is an interaction that is going to be from stirrup also, because that is arresting both the shear as well as torsion. Now, what is Ts contribution? So, that is again given by this some equation, which is 2 Ed by 2 Ed plus x1 into y1 into this. So, if you substitute that, you get your torsion contributions as Tc naught plus this. So, this is your Tc and this is your Ts. So, this you see we are adding all this. So, just like for shear we do Vc plus Vs, for torsion also I do Tc plus Ts. Okay. So, if the values of r and psi and alpha is substituted for common range of sections, then r becomes r naught as this, and then if you substitute psi is equal to T by m and alpha is equal to h by b, like what we have seen, and if you assume some values for mode 1 failure. So, this is why it is important. So, finally, we wanted to prove that m naught is nothing but m is equal to m plus t into square root of 1 plus t alpha, or in other words, for mode 3 same way, m naught is this. So, finally, this is what we want. So, this is basically, see, for this is from flexure and this is from torsion. Now, both have to, I have to design the steel in the tension side, so that the flexure effect also will be resisted, the torsion effect also will be resisted. So, that is why we derive this expression for your m naught in terms of m and t. Similarly, for mode 3 failure, this is the same thing, right. So, similarly for mode 2 failure also, I have this as this. Okay. So, that is how we do this. So, for example, so this is nothing but your MT in your calculations. Okay. So, this is your flexure, this is your MT. Similarly, this is your MT, that is what we use. Okay. So, this is again similar to your MT. So, that is what we do. So, what we are really doing is we are converting the torsion into an equivalent bending and design for it. Okay. So, that is what we are doing. So, let us look at it now how. Now, for equivalent moments, let us see now how do we do it. So, the equations that are given in IS 1343 are applicable for beams of following sections. What are those? It is applicable for solid rectangular sections with depth greater than width, for hollow rectangular sections with depth greater than b and the thickness should be at least b by 4, and for flange sections like T beams and I beams. Now, what are equivalent moments? This is what I said. First we are going to convert the torsion into equivalent bending moments ME1, ME2 and ME3. Now, ME1 is the again is, you see, this is from flexure, this is from torsion converted to flexion. Okay. So, that is why I said. So, now bending is going to create compression and tension, torsion is going to create tension everywhere. So, at one location on the tension side, the amount of tension is going to increase. So, somehow I have to account for that. That is the reason the torsion is converted into an equivalent bending moment. We have increased the demand in bending and then we are designing for it. Now, ME2, when it is will come, when the torsion is very high, now the top compression force will be nullified, then the top can also get into tension. So, that I am designing it as a negative bending, that how much I have to design, that is MT minus MU. So, whenever MT becomes higher than MU, then I need to design for this ME2. Now, what is ME3? ME3 is your again the lateral bending failure mode, which is MT into this formula. So, this is a function of your the aspect ratio of your section, right. So, if you have very slender section, so then you will have failure in lateral bending failure mode, or when your width is very less compared to that of depth, then this kind of failure mode that you can have. Now, how do we convert the torsion into an equivalent bending moment? So, this is what it is. So, this is what we have, and ME3 will be critical when the beam is very slender and narrow and height to width ratio is very large. So, this is where ME3 will be controlled for a very slender beam. Now, especially we have to be very careful, particularly when you go for very high strength concrete, and typically we tend to provide less web width, but more depth. So, in that case that ME3 mode also can become critical, we need to be careful. Now, transverse reinforcement. So, what is the interaction between shear and torsion that we have already seen? You will have the interaction between the ultimate torsion to cracking torsion and shear ultimate to cracking shear can be expressed like this, and this is a basic equation of interaction, and we define the loading ratios as Tu by Vu as E and Ec as Vc by Tc by Vc. Now, this is what we said. This is your pure torsional capacity in concrete capacity in torsion. Now, when you have combined shear and torsion acting, somehow I have to reduce this. So, this is some kind of a reduction factor. So, this is also some kind of a reduction factor. Okay. So, this is Tc is reduced to get Tc1, Vc is reduced by this factor to get Vc1. Okay. So, the expression for again Tc can be either derived through plasticity theory or through your thin walled tube theory that we have discussed. So many expressions are there for Tc. So, that whatever is prescribed by the code we can just use it. So, this is how it works out to be. TC is 0.15 B square C B square into D into 1 minus B by 3D into this, and this is the effect, the factor that takes into account the effect of pre-stress is taken into account, right. And VC is again, as I said, smaller of both this. Again, this is web shear and this is flexure shear, right. So, we take calculations of this and then whichever is the minimum, that we consider that as a VC, right. Now, what is in terms of transverse reinforcement? Again, transverse reinforcement we have seen AV is the stirrup for shear and AT is the stirrup for torsion. Now, you see when I have two legs, when I calculate it, right, now torsion will be twice the area that I am providing, right. So, that is the reason we are multiplying by 2 here, and AV, the stirrup required for shear will be V minus VC1 into S by 0.87 Fy into D1, and AT will be T minus TC1 into S divided by 0.87 Fy into D1, right. Now, what is the minimum reinforcement? Same thing that is applicable for shear, 0.4 by 0.87 Fy, and these are the things. Now, you see the spacing SV is if we take B1 as the dimensions between the in the horizontal direction, the center distance between the farthermost longitudinal bar is taken as B1. Similarly, D1 is taken as the center line distance between the longitudinal bars which are farther apart, which is D1. Now, what is x1 and y1? x1 and y1 are the distances between the center line of the stirrups, both in the x and y direction, right. So, the SV has to be less than x1 or x1 plus y1 by 4 or 300 mm. So, you see here x1 is measured center line of the stirrup in the x direction, similarly center line of the stirrup in the y direction. So, and again for whenever the depth becomes more than 450 mm, see in flexure when the depth becomes more than 750 millimeter, in RC, in B when no torsion, then side face reinforcement, right. However, moment you have torsion, even when the depth is just above 450 mm, the code is mandating you to have some side face reinforcement. The reason is the torsion is going to create tension on all the 4 sides. You saw that spiraling crack. To tackle that, we need both stirrups as well as longitudinal bars. So, that is the reason the code is asking us to provide, even the depth is for more than 450 mm, we need to put side face reinforcement. And what is the amount of side face reinforcement? It should be at least 0.1% of B into D, and maximum spacing should be 300 mm or B, whichever is less. And also there should be at least one longitudinal bar in each corner like this, okay, and we should have, and the minimum diameter of the longitudinal bars is kept as 12 millimeter. Okay, these are all some requirements. Okay, so this is similar to what we did for shear. It is this, only we have to now include some interaction effects as well.